right, and now let's go over to question 2. And just a note on question 2, I actually finished filming the video, and then I realized that the actual calculus book had a mistake in it, and then I thought I might as well redo this and add more clarity, even though the final answer is still the same. So question 2, the volume V of a tetrahedron is 1/3 the distance from a vertex to the opposite face. And here's the correction, MES correction. This is actually the height of the tetrahedron. So it's not actually the distance from a vertex to the opposite face, but it's the height of that tetrahedron from this opposite face. And I'll illustrate that in a bit. So times the area of that face. And again, I will look to provide a proof in a later video. And now look at question A. So question A states find, or part A of question 2 states find a formula for the volume of a tetrahedron in terms of the coordinates of its vertices P, Q, R, and S. And then part B states find the volume of a tetrahedron whose vertices are P, 1, 1, 1, and then has Q is 1, 2, 3, and then R is 1, 1, 2, and then S is 3, -1, and 2. So let's take a look at solution to part A. So after finishing the filming of this video, I realized that the formula for a tetrahedron as stated in question 2 is actually wrong. So that's not actually the formula. The actual formula, and here I added a link to the Wikipedia article, involves the height of the tetrahedron and not the distance from vertex to opposite face. And this is evident from a skewed tetrahedron. And here I'll draw it out. So let's say we had a tetrahedron like this, something that's not symmetric like this. And yeah, so let's say there, and then inside there's the point like this. So there's the inside triangle, and there's the 3 triangles around like that. And let's say there's an area here in this base there. And so the opposite vertices is somewhere here. So the distance from this face to that is going to be, well, something like that. But that's not actually what we want. The actual formula involves the height, h, like that. And the volume of this tetrahedron is equal to V, 1/3 the height times by that area. So this is the volume. Yeah, so it's equal to, yeah, so 1/3 the distance is actually, it's actually the height. So 1/3 the height times the area of that face. So from this area up to there. So that's the actual formula. All right, and going further, I think what the Discovery Project actually meant was the distance to the plane that contains the opposite triangle face, which is the same thing as stating the height of the tetrahedron. So this distance right here is the same as saying that the distance from this point to the opposite face, or to the plane that consists of this opposite face. If we had a plane like that, just have it in 3D like that, and this triangle is inside this plane. So the distance from that plane that contains a triangle to that point. I think that is what they were considering. Let's erase all of this. All right, so yes, going further. So thus we can write the volume of a tetrahedron in coordinate form as follows. And first what I'm going to do is I'm going to actually draw that skewed tetrahedron again, just so it's more clear. So that, yeah, we're not dealing with, yeah, so we're dealing with the height. So let's just draw this out. I'm going to draw it like this. And there is our triangle. And then inside has a point, say this point like this. And I'm going to call the point inside here, I'm going to call it P actually, instead of the S. I'm going to say this point S. And it has coordinates S1, S2, S3. And then let's say, and then the height here, or the distance to the plane that contains this face right there. This is going to be our H, like that. And then this point right here is, let's say this is our R. It says R1, R2, R3, and then this point right here is going to be, let's call this Q. And this coordinates are Q1 lowercase, Q1, yeah, Q1, Q2, etc. And Q3, and then at this point right here, we will call this point P. And I'll put this like this, so that is our P. And the coordinates are P1, P2, and P3. Like that. Alright, so now that we have this set up, so we could write the volume as, so we could write V equals 1/3 H times by the area of this opposite face, which is P, the area of this PQR triangle. And now what this equals to, well, let's write down our terms. And then the height is, let's call this, let's write this in terms of the distance to the plane, just so it's generic. So distance, we'll call it d, from the plane. So we're going to go from this point right here. So we'll go from S1, S2, S3, and then that distance all the way up to the plane that contains PQR. Like that. And then the area of this triangle, we know that already. That's just this vector right here, this PQ and this PR. And I'll just put this P as well there. And the coordinates are P1, P2, P3, etc. And so we have this. I'm going to shift this over like this. And then now this one here is going to be multiplied by the area of this. And then we already solved that earlier, is 1/2 the length of the cross product, PQ cross PR, like that. All right, and now I'm going to box this in, and the solutions that I found online, I couldn't find the solution manual. The solution I found online just stopped at this point, but I'm going to keep going further and get the exact stuff they're asking for, which is in coordinate form, because this one just says, well, the distance and so on, but we don't have a formula yet for the distance. All right, and now that we have this, let's just keep going further, and we're going to look at now the equation of a plane, because here we have distance from this point S, from the point S to the plane PQR, or that contains this triangle PQR. So let's write the equation of a plane. So note that the equation of a plane can be derived based on the fact that the dot product is equal to 0 for perpendicular vectors. And yeah, I haven't covered equation of a plane before, so it's a good time to start now. What I'm going to do is let's just draw a plane like this. And when we talk about plane, just basically a rectangular in 3D rectangle, etc. And now what we're going to do is I'm going to put the x and y axis, put it like this. So that's y, and there is our x. And this is our z. There's the origin, 0. And let's say we had a point here. I'm going to call this point over here is at x0, y0, z0. And let's say there is a just vector like this. And this goes to the x, y, z, and a point right here. So it's a vector like that, and this could be anywhere. So that's the whole idea of a plane. So anywhere around this perfect rectangular sheet right there. And now, and then this can extend to infinity, etc. if it's not bounded. So now what we'll do is we're going to use the fact that the dot product is equal to 0 for perpendicular vectors. So if we take a vector perpendicular to this plane, like this, so this is, let's say this is perpendicular, and we'll call this n, or normal to it, or perpendicular to it. And let's say this has the components for this vector, capital A, capital B, and C, like that. Yeah, so thus the dot product of this of these two perpendicular vectors, where we can get the position vector over from here to here by subtracting. So what we'll get is, well, we'll go A, capital B, capital C, dot, and then the position vector of this vector right here. Position vector, all we do is shift it over to here, etc. And likewise for this one there. Yes, and this vector right here, this is actually the position vector. So this is the same thing as over here and so on. So, but these ones have the coordinates, so then we could get the position vector, and let's just write that down, and that's going to be, well, just the difference, x minus x0, and then y minus y0, and then z minus z0, and then recall from my dot product video, if they're perpendicular, that's equal to 0. So, and now we could just do the dot product. Remember that, we just multiply this by this, b by the middle, c by this one, add them all up. So we just multiply by the components and add. So what we get is a x minus x0 plus b y minus y0 plus c z minus z0, and this equals to all 0. And you can stop right here or continue further. I'm going to continue further and simplify it. So that's one way of writing the equation of a plane. The next one is you can expand this out. This equals to, well, a times x, then minus a times x0, but we'll do that after. So a times x, and the next one is b times y plus c times z. B times y plus c times z, and then minus, when we do this all together and add those up, we'll get this ax0 plus then this b times y0, and then c times z0. Like that, this equals to 0. Alright, so now that we have this set up, and what I'm going to do is, well, I'm going to call this lowercase d, and then just write this out as ax plus by plus c z minus lowercase d equals to 0. So this is the equation of a plane that's usually given. Alright, so now that we have the equation of a plane here, now the next step is, well, we need to find the distance from a point to a plane, because remember this is the distance from the point S to the plane PQR that contains the triangle PQR. So, and the equation for the distance from a point to a plane which I'll prove in a later video, is given by, just a bit out of the scope for this video right now. And let's just put this down here. Let's just do some drawings again, just to make it clear. Let's say we had a plane like this, this angle like that. So this is a plane, and this has the equation ax plus by plus cz minus d equals to 0. So let's say we had like that, and let's say we had, this is our y, this is our x, and this is our z, like that. 0 point. Let's say we had a point P. Let's say the point P is here, and this point is has x. Or instead of just putting a point P, because we already have P for something else. Let's say this is x1, y1, and z1, like that. All right. So now the distance from here all the way to this part right there, it's going to be perpendicular to it. So let's just draw this a bit better. So let's write this plane here. And let's say this point like this goes across, let's say it goes all the way across here, and it's going to be at a right angle to it, because it's that's the closest distance to it. And this point right here, we'll call this D. So from there, or from this distance, like that, let's call this D. Like that. So that is the distance d, and d is given by the formula, which I'll prove in a future video, ax1 plus by2, by1 plus cz1 minus lowercase d, divide this by square root a squared plus b squared plus c squared, like that. That is the distance d. And let's bold all, or box all this in. Alright, so thus putting this all together, the volume of a tetrahedron in coordinate form is, we're going to have v equals to, well, 1/3 the distance to the plane, or the height, and we'll put a giant bracket like this, a, and instead of this x1, y1, z1, we're going from the point s1, s2, s3, etc., to the plane PQR, and there's the area of that triangle. So that's going to be S1 plus B S2 plus C S3, and then minus D, like that. Divide this by, this is going to be A squared plus B squared plus C squared, and then bracket, and then this is the area of the triangle. It's going to be 1/2 the length of the cross product PQ cross PR, like that. And yeah, that's what we have. Let's just go look at the formula we had. So there's distance, and there's the 1/2 PQ times or cross PR, which is quite fascinating stuff indeed. I'll move this into center. And yeah, this is some epic stuff right here. And I'm going to do is I'm going to box this whole thing in, or actually box the entire volume in, like this. All right. And then I'm going to write here, because we need this A, B, C, etc., where the ABC, well, that is, again, that's going to be from a vector perpendicular to this plane. Because remember this equation right here, perpendicular to the plane. In other words, if we go back up here, it's, well, we have a perpendicular plane right there. That's our N. There's our PQ, yeah, PR. So in other words, it's a cross product. So this is going to be where PQ cross PR is going to be, oh, this is a vector, equals to, well, just the vector A, B, C. And we're also given, so we're that, and we know that this D is equal to, well, if we go back up, what D is A x0 plus B y0 plus C z0. And again, if we go back up here, so we have this point, this is our N. So this is going to be our P there. This is going to be our x0s, y0s, etc. So that's our N. In other words, that's going to be this point right here. That's just the point P. And that's where we take the cross product from. So then we replace the x0 with the P coordinates. So that's going to be where D is equal to, well, A, this is going to be x1, P1. P1 plus, for our case, B, P2 plus C, P3, like that. So that is our D. And we can illustrate this by, and actually before that I'm going to do where, I'm going to box this in. So this is part of this equation. So this throws it all inside. And then note, just to illustrate that, draw our skewed triangle, or tetrahedron, is like this. This is point S. Point P is inside. Goes dashed line across. And then this is going to be a dashed line across. And this is our R. This is our Q. And then our cross product goes up like this and goes straight across it like that. This is our N, like that. And there's our point P. And this N is again equals to, let's put this N like this. Let's move this down. Yeah, move this down. And yeah, write this back again. So N, and that is our perpendicular vector, and that's just going to be the PQ. So PQ from this angle, from this this vector to this vector, cross those, and we get cross PR, like that. So yeah, that's what it is. Alright, so now that we have this, and yeah, this is more detailed than the solutions that I was able to find online, but they weren't the official ones. But anyways, it's pretty in-depth. You could even throw this in a computer program and solve it all. Alright, so that's what we have. So let's go back to, well, question, the part B of it now. So question 2, part B, says, find the volume of a tetrahedron whose vertices are P111 and Q123 and R112 and S3 minus 1, 2. So let's write these down and start solving it. So solution to part B. So the first step is to derive the position vectors PQ and PR and then compute their cross product and cross product length. So, well, let's write the point P is 1, 1, 1, and then the next point is Q is, well, 1, 2, 3, and then R is 1, 1, 2. And we'll deal with the S later. So let's just double check that. And double check it is 1, 1, 1, 1, 2, 3, 1, 1, 2. All right. So that's what we have. And the position vector PQ is just a difference Q minus P. So we're going to have write this in vector form, the square bracket or the triangle bracket. So 1 minus 1, 2 minus 1, and then 3 minus 1. Like that. And now this equals to, well, 1 minus 1 is 0. 2 minus 1 is 1. 3 minus 1 is 2. That's position vector for PQ. The next one is PR. Alright, PR is equal to, well, 1 minus 1. And then we'll have this 1 minus 1. And then 2 minus 1. And now this equals to, well, 1 minus 1 is 0. 1 minus 1 is 0. And 2 minus 1 is 1. Alright. Alright, now that we have this right here, let's solve the cross product and then do the cross product length afterwards. Because again, we'll need the cross product for this, ABC, and then the cross product length, that we need that for this area there. So let's write this down. So PQ cross E r is equal to, and then write this in indeterminate form. And let's move this down a bit because we're going to write this in the giant determinant. I, j, k, like that. The next one's going to be 0, 1, 2, then 0, 0, or 0, 0, 1, like that. Alright, this equals 2, well, let's just solve this out. So again, as always, you cross this, and then you multiply this by this, and then subtract by this by 2 times 0. So we're going to have a 1 times 1 minus 2 times 0, 0. This is going to be the I component. Alright, erase this. Now the next one is here, so we'll do a minus. The middle one's always minus. So 0 times 1 is 0, minus 2 times 0 is 0. J, and the next one's plus. Erase this. Cross this. The next one's going to be 0 times 0, minus 1 times 0 is also 0. This would be k, like that. Alright, that's what we have. Alright, so that's what we have, and now we get to simplify this further, get rid of all the zeros. This is going to be, well, I. So 1 times 1 is, 1 times I is just I, or 1I. And all others vanish, and that's all we're getting, is just the I component. In other words, in writing this in the other component set up like this just equals to 1, 0, 0, like that. And where again, this cross product is going to be, we're going to need it for our equation. That's just our A, B, C. In other words, all the B and C are 0, and then A is 1. So that's what we have. And now the area PQR, remember this is just going to be 1/2 the cross product length. 1/2 cross product length, like that, PR. And this is going to be equals to, well, 1/2 of the length of this this vector I, which is, well, again, this is just going to be 1/2 square root, and then 1 squared, all the components squared, 0 squared. Well, 0 squared, these all vanish, it just becomes 1 squared, this is 1. This is equals to 1/2. So the area is 1/2. Like that. Alright, so now that we have this, the next setup is to find a distance from the point S, which has coordinates 3, -1, 2 to the plane, PQR. So let's write this down. So we have our points, this S right here, this is a 3, -1, 2. In other words, this is the coordinates S1, S2, S3 that we were looking at. And that is for the equation. So there's S1, S2, S3. And we already know what ABC is. ABC is this right here. Yeah, so let's just write that down. So we know that the normal vector of the plane is equal to, in our case, PQ cross PR. And this equals to 1, 0, 0. And then we have it, this equals to, well, A, B, C, like that. Yeah, in other words, we have A equals to 1, and B equals to C, which equals to 0. So let's just circle these like that. That's what we have. And then we also have this right here. And then the next setup is, well, we need to solve our D. And this is the point P. And the number of the coordinates of P is just 1, 1, 1. So let's write this down here. So we also have, let's just write that down. So P, this is P1, P2, P3. This equals 2, P1, 1, 1. All right, so we have that. So all those are equal to 1, 1, 1. So so then this means that the lowercase d is equal to A P1 plus B P2 plus C P3, and A is again just 1, so 1 times 1 plus, and then B times, well, B0. This is equals to 1, like that. Alright, so that's D is equal to 1, so in other words, we'll have this right here, the distance D is equal to, that distance is just this whole part right here, and we already know that D is, etc. So let's just write that all down. A S1 plus B S2 plus c as 3 minus d. Divide this by square root a squared plus b squared plus c squared. This equals 2, and then a is just 1 times s1 is 3. Minus, plus, and then b is 0, plus c is 0, minus d, d is just 1. Like that. And then divide this by square root, a squared is 1. Yeah, I mean, a squared is just 1 squared, plus all others are 0 squared. 0 squared. So in other words, all we get is, well, this becomes 3 minus 1 over 1. Because this is just 1 squared and then square root. This equals to 2. So the length is 2. All right, and so the distance from the point to the plane is 2, but we can do a double check right here. Let's do a double check. That was using the equation, but first we got to find the equation of a plane. So we have the plane is just going to be, well, if you just remember it, ax plus by plus cz minus d equals to 0, and d is just 1. Then a is just, we already know a is just 1, everything else 0. This becomes 1 times x minus 1 equals 0. So in other words, we have x minus 1 equals to 0, or x equals 2. Shift the 1 over to the other side, x equals to 1. So this is the equation of a plane in 3 dimensions. All right, so let's graph that out. So let's say we had the plane like this. I'm going to draw this plane like this. All right, so that's the plane, and let's say we had this point goes out like this. This is the x-axis, goes through and over here, and this is the y. I mean, this is the z, I mean. And at this point right here is 1. So that's x equals to 1. So this is the x equals to 1 plane. And this is our y, like that. And let's say our point was the 3, or our point S is going to be, well, 3. Let's say this is 2. Let's say this is 3 now. So this is 2 here. And then it goes -1. So here, like that, -1. And then it goes up to 2. Somewhere around here. And this is our point S. I'll put point S. Point S, which has coordinates 3, -1, 2, like this. And basically what this is saying is, well, the distance from here to here, perpendicular to it, is just going to be directly across on this x-axis, because this is perfectly straight with this x-axis. That's going to be this 3 minus 2. I mean 3 minus 1 equals to 2. So we have double checked that. That's exactly it. All right, now that we double checked that, let's write this a bit better, like this. And now the next step is, well, let's just put it all together. So thus the volume of the tetrahedron is, and write this out, so V equals to 1/3 times d, the distance from, well, the point S to the plane. Let's put these all down, PQR, and then times it by the area of the PQR. Area PQR, this equals to, well, 1/3 times the distance can be 2, times it by the area, number is 1/2, and yeah, just to double check. So there's the, this is the distance 2, area is 1/2. And these 2 cancels, and this equals to 1/3. Epic stuff. All right, and now let's go even further, and let's, as a double check, we can graph the tetrahedron and calculate its area using the GeoGebra, or just using GeoGebra, which is an amazing 3D graphing calculator and other kind of calculator here. So here's what I've graphed. So here's the points P, Q, R, and S, and then I made a pyramid, PQRS. In other words, just a triangular pyramid is a tetrahedron, and then we get something that looks like this, and it actually calculates area too. Area is equal to 0.33. In other words, 1/3, so we got that right. And then when you shift this around, and you see this perfectly in line with the x equals to 1 plane is the x-axis, this z, there's the y, etc. And also note that, again, if you have this plane here, notice the distance to the point S, or the perpendicular distance, or the height from the plane, is exactly 3 minus 2. So this 3, this 1, so this distance is just 2. Yeah, so that's just 2. So yes, epic stuff here. And now if we go to this link, so here's a link, you can play around with it, and so on, and it looks like this, and you can move it around, and so on, which is quite amazing. And you can adjust it as well. You can move this. I think you could also drag and drop. So you can change it around, and you see the area automatically changing, and so on. And let's do a Control Z back there. Yes, epic stuff. And again, notice perfectly in line with the with this right here, with this x equals 1 line, and there's a distance 3 minus 1 is 2. So that's the height. Yes, epic stuff.